we're going to talk about sequences and series. So all this, as things get hard and complicated, you can never lose sight of these basic ideas that we're going to cover today. If you lose sight of the basic ideas today, then you're just lost all to pure memorization. And if something's a little bit different, your memorization's not going to get you to the goal. So understanding of the basics, today's lecture, is super important for this whole next component. And so that being said, a sequence, whenever we talk about a sequence, you have to have in mind that what is this? It's simply an ordered list of numbers. A sequence is an ordered list. We just make a list of numbers. Most of the time, there's a pattern to that list. Okay, but it doesn't have to be. There doesn't have to be a pattern. Okay, and so then a series is where you take that list and you add up the terms in the list. That's what a series is. So first and foremost, these two ideas, these definitions, you have to be solid with this. So when you're getting into the nitty-gritty, you know exactly what you're working with. So we make a list called a sequence, and then when we talk about the series, we're taking all the terms of that sequence and we're adding them up, making a sum, adding them up. Okay, so our notation for a sequence is this. I call them chevrons. Okay, so we've got brackets and parentheses and braces. For a sequence, we use chevrons. Okay, and then what's this A sub I? How does this work? So what we're saying is that I is called the index. I is telling us which number of the sequence it is, or which number of the list. So there's the first term of the sequence, so we use I equals 1. And then there's the next term in the sequence, so I equals 2. And so that's the subscript. So then A1 is the first term of the sequence, and A2 is the second term of the sequence, and then A3 is the third term of the sequence. Does it make sense? So you could generically say A sub n, that's if you go out n terms, that's the nth term of the sequence. So here's an example. The sequence starts with 1, and then 3, and then 5, and then ellipses means continue this way. Just continue this way indefinitely, ... Just keep going. So what is A3? What is A3? Someone said 5. Do you agree with that? 5. A3 is 5. Okay, so now, if this same pattern continued, what would A5 be? What would A5 be? Someone said 9. Agree with that? It'd be 9, right? It'd be 9. A5 would be 9. All right, what about A85? Not immediately known. How about that? Not immediately known, but we could figure it out if we had time. Or instead, so rather than sitting there and counting out 85 terms and saying, oh, we finally got there, what about finding a formula that gives the nth term? So given that you're talking about the nth term, in this case the 85th term, is there a formula based on n that would spit out what the 85th term would be? So here's a helpful way to, and this is going to be part of some practice problems that you'll have, where you'll be given a list and you have to figure out what formula gives the nth term of the sequence or of the list. So here's a technique that's helpful. If you make a table, that's pretty, but let's use black. So if you make a table and write I and then A sub I over here, and you might not have to do this for everyone, but this is a nice technique that may help you to see or make progress towards finding the formula. So I always starts at 1, because again, this is the which term of the sequence is it? So we're going to have the first, and then second, then third, then fourth. Later on, when we get in further, I can start at anything. But for purposes of introducing sequences, I will always start at 1 because I will always represent how far down the list did you go, right? Are you the first term, are you the 9th term, 11th term, whatever. All right, so we got a sub I is 1 for the first term. Second term is 3, 5, 7, 9, etc. And so now the table kind of helps you see maybe what would you do to the value in the left column to always get the value in the right column. So everyone think about it to yourself. See if you can figure out what would you do to the number on the left side that would always be the same to get the number on the right side. So this is an easy one. Hopefully everyone can get this. What would you do? You notice this is 1 less than twice this number, right? So you'd multiply this by 2 and then subtract 1. Do you see that? So that's the kind of thinking that has to go into this. Like, hey, what would I do to this? Let's say 3 gives 5, 4 gives 7. Oh, this is always like 4 times 2 is 8, 3 times 2 is 6, 2 times 2 is 4. So there's always 1 less than 2 times the I value. So this is how we would write this. So we would say the sequence is, a sub I is 2i minus 1, where I starts from 1 and then just keeps going, right? Never ends. Let I be every value starting from 1. And that will create the sequence 1, 3, 5, the odd numbers, right? The odd numbers. So now, what's A85? Now it's easy. You see? What's A85? 169? Piece of cake, right? Fast. Anybody have a question? So what is the sequence? It's a list of numbers. Most of the time, there'll be a formula that generates that list, but it doesn't have to. It could just be a random list, okay? And then we've talked about the notation here. Yeah.
How would you do the same? But how would you solve that problem if it was not in a specific order? If it was random list?
Then there wouldn't be a formula. If it's truly like a random list, then there is no formula. Is that what you're... What's that?
So there's like no...
Well, yeah, so if there's a formula, then it wouldn't be a random list. There would be a pattern to it, according to the formula. So if it's just, if I could create a sequence like pi, 100, negative 32, 1/2. That's a sequence. But there would be no formula that would get you that. There's no formula that would get you the same, for the first term give you pi, and the second term give you 100, and third. So there would be no formula to find. But it's a valid sequence, nonetheless. Does that answer it? Okay. All right. Okay, and so then this kind of should be like the idea of a function, right? So the independent variable is what? Independent would be what? I, right? Independent variable would be I. And then your dependent variable would be whatever the term of the sequence is, right? So this idea that there's a formula to generate the terms based on where you are in the sequence, I, that's the feeling of a function, right? So we could write that. Instead, we could write the sequence as a function. We could say a sub I, right? So this is the name. Name of the function, independent variable. What represents the dependent variable? What represents the dependent variable? Okay, that's the rule. Okay, that's the rule. But if we wanted to represent values of the dependent variable, how would we represent values of the dependent variable? Please know this. We've been working on it all semester. What's that? A of I, right? A of I. Function notation, right? Function notation gives values of the dependent variable. Function notation gives you values of the dependent variable. We've been working on that all semester. But here, I is not all real numbers like we're used to. It's not a continuous variable. So we have to specify that we're only talking about the I values 1, 2, 3, 4, etc. And once you do that, then this function is absolutely equivalent to this sequence. You see that? So now this function specifying these I values is totally equivalent to this sequence written that way. Are we good? Any questions? So let's have you practice some formula creation on some harder ones here. Oh, no, one more thing to talk about. So infinite sequence has no last term. A finite sequence has a last term. So that example, the pi, negative 100, negative 32, 1/2, that was a finite sequence, 4 terms. If it's dot, 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 or you go I equals 1 to infinity, that's an infinite sequence, no last term. Okay, so let's find a formula that gives the ith term of the sequence. So there's 2 practice problems. First one's a little bit harder than the example we did. Second one's a little bit harder than that, but these are both attainable. You could do it. So I'm going to start taking attendance. See how you do. Encourage you to work together. So either you're making progress by yourself or you're working with someone else and getting help. So write them out first. So write these both out first. Because I'm going to take them off the screen for attendance. So if you didn't here's some hint. The hint for the first one is ignore the negatives at first. Take care of that at the end, and then solve the numerators and the denominator separately. So if you had those 2 ideas, that was good, right? So ignore the negatives, figure that out at the end, and then work on the numerator and the denominator as 2 separate problems. Okay? And then your hint on the second one is focus on 3, 5, and 7. See if you can come up with it for 3, 5, and 7, then go back and check 1, 2, 4, and 6 to see if your formula works. Okay, how do we do on this first one? So just forget about the negatives and look at the numerators. The numerators are 3, 5, 7, 9, 11. Oh, so notice they're not all called A, right? So just like functions, we can call it anything we want. F, G, H, P, Q. Same with sequences. A, B, C, D. So any name is fine. Okay, so this one's our B sequence. Okay, so numerators 3, 5, 7, 9, 11. How do we do on that? Zoe, did you get that?
I didn't get the negative.
So I'm just talking about, without the negative, just talking about the numerator, 3, 5, 7, 9, 11. Did you get that?
Yeah.
She wants 2i plus 1, agree? So similar to the odds, but it's like they're all shifted, right? So like instead of 2i minus 1, now if you multiplied by 2 and added 1, you'd get that. Everyone got that? Okay, denominators. 1 gives 4, 2 gives 9, 3 gives 16. So first of all, those numbers 4, 9, 16, 25, 36 should ring a bell there. Those are squares. So are they I squared? No, so this is 2 squared, and we're at I equals 1. This is 3 squared, where I equals 2. So what square is it? Jennifer, did you get it?
I plus 1 squared.
Yeah, so you had to add 1 to the index first, and then square it. Any questions? So that's the numerator and the denominator. Okay, so now how do we get this thing to, basically when it's odd, we get negative, and when it's even, we get positive. Anyone come up with a way to do that? Yeah, Nick. So if you take -1 to the ith power, does that do it? Odd powers, if you multiply -1 together an odd number of times, it will be what? -1, right? But if you multiply it together an even number of times, you get +1. Does it work? It works, right? Okay, that's the most common way to do it. So this is the most common way to get, this is what's called an alternating sequence. Alternating means it alternates positive, negative, positive, negative. So anyone else come up with a different way? So this is the most kind of common way to create the alternating sequence, that it switches from negative to positive. Anyone come up with another way to do it? What other kind of thing kind of cyclically jumps back and forth? In all the functions we've encountered in your calculus and pre-calculus career, what kind of function has a repeating pattern? What's that? Yeah, so tell me. So if we wanted 1, then -1, 1, then -1. What kind of function gives 1, then -1, 1, then -1? Is it familiar? Cosine, right? Cosine gives 1, then -1, 1, then -1. Okay, so this is at 0. Where does it give -1? Pi. Remember your trig functions. Back to 1 at 2 pi. So how can I use cosine then? So this is the cosine. Cosine of what related to I? Is it cosine of I? No, not cosine of I. But cosine of what would give me cosine of? So when it's 0, we get +1. So when it's 1, we get -1. Pi times I, right? See that? So this is another way to do this that you have to be on the lookout for. 1 pi gives -1. 2 pi gives +1. 3 pi gives -1. 4 pi gives +1. So this does exactly the same thing as the -1 to the I. Do you see it? Also, you could do it with sine. You could do it with tangent. Those are all any repeating type of function, like a trig function, could be finagled to give you -1 on the odds, +1 on the even. Cosine's the easiest one. Cosine just fits the bill. The other ones you have to do a little more work. Did you get it to work? Okay, questions on sequence B? Yeah, so either that or, so this first part, or -1 to the I. Both those work for that first, to get it to go -1, +1. Okay, how about this next one? Anyone have progress with this? What green? So we got I and CI. So 1, 2, 3, 4, 5, 6, 7. And so I told you to focus on, as a hint, 3, 5, and 7. So 3 is 4/3. 5 is 16/5. And 7 is 64/7. Again, we're going to break it down. Look at the numerator separately and the denominator. So 4, 16, 64. What are those? So what are 4, 16, and 64? Well, those are perfect squares also, but they're also something different than perfect squares. Anyone figure out what those were? Yeah, they're all powers of 2. Do you see that? So this is 2 to the power of what? 2. 2 to the power of 4. 2 to the power of 6. So comparing those powers, 2, 4, and 6, to the I value, 3, 5, and 7, our numerator is 2 to the I minus 1. Did you get that? How many people got that before we started doing it? A few. So these are powers of 2, and the power of 2 is always 1 less than what the current I value is. So 2 to the I minus 1 is the numerator. All right, denominator. 3, 5, 7. Yeah, so when I is 3, you get 3. When I is 5, you get 5. When I is 7, you get 7. So it's just I. So now what we can do is go back and check when I equals 1, 2, 4, and 6, do we get the right thing? So I is 1. When I is 1, we get 2 to the 0 is 1 over 1 is 1. Check. When I is 2, 2 to the 2 over 2 is 1. Check. See what I'm doing? How about 4? 2 to the what? 2 cubed. So 4 minus 1 is 3. 2 cubed is 8 divided by 4 is 2. Check. Working. Last one. 2, 4, this is 6. 6. 2 to the 5th is 32. Divided by 6 is 16 thirds. Check. So we got it. 2 to the I minus 1, so CI. To the I minus 1 all over I. Okay, so we're going to have web work in this section. So in web work, you're going to have where you're figuring out formulas like this. Any questions on these two examples? Last chance. Okay, remember, a sequence is the list. What is a series? Series is where you take the list and you add them up. You add up the values in the list. So given the sequence, our first one, A, 2i minus 1, the series from the sequence is the sum of all its terms. So for this sequence, I want you to write out the series in a way that a second grader would understand it. Write out this series corresponding to this sequence in a way that a second grader would look at it and understand it. Can you do it? Write something that represents the series for this sequence that a second grader would understand. Because if you can do that, then you understand it. Then you understand it. Okay? If you can do that, then you understand what a series is. What's that? No, I'm asking for this series. The series. This odd numbers, that's the sequence. That's the sequence. If you say the odd numbers, you're talking about the sequence. So I want you to write out the series associated with that sequence in a way that the second grader would understand. So McKay, were you able to do that? What about you, Thomas? What is a series? This goes just, what is a series? It's the sum of the terms of the sequence. So how would you write that for a second grader? No, second graders have no idea what summation is. They have no idea what summation is. That's the whole point. Second graders don't know sigma, right? So what is it? Right. 1 plus 3 plus 5 plus 7 plus etc. Okay, so that's how a calculus student understands it. So now we want to write it as a calculus student would understand it. How would a calculus student understand that? This is where we pull out the sigma notation. Right? So we did that earlier in the semester, right? When we were talking about developing the integral, right? Summation notation. This says start at 1. Start at 1. And put 1 in there. Then make it 2 and put 2 in there. Then make it 3 and put 3 in there. And then do what? Add them all up. So here's the whole ball of wax with these series. You see this? When you see this, what? You think, or we're going to write it a lot too, but you're going to think this. If that's what's going on in your brain, then you understand what a series is. You understand what a series is. You see something like that on the left, you think, oh, that's a sequence, and it's telling me to add up all the terms in the sequence. But in order to have this mentality, we're going to be writing out that a lot. So lots of times I'm going to show you this, and I'm going to say, first I want you to write out what it means. Write out what that thing means, and you'll write out the sum of terms. Okay, or it's this equivalent to this, the sum of just, you could write AI, because this AI is the sequence 2i minus 1. So all those mean the same thing. So I want you to write out the series associated with sequences BI and CI that you did in the practice for writing the formulas. So then I want you to write out each of those in the way that a second grader would understand, and then in the way that a calculus student would understand. Okay, I'll just write out CI. I trust you can do BI. So I'll just write it out for CI. So Jose, did you get it? How would we write the series for CI in a way that a second grader would understand? Can you tell me? Oh, okay. Can you just look at CI and do it on the fly? Right. Plus what? What was it? Oh, plus 2. Is that right for CI? All right, now we want to write it out for a calculus student. Summation. Good. Good. So those mean the exact same thing. They mean take all the terms of the sequence and add them all together. And then we could also just generically use CI in there. Okay, so yes, you have to be good at interpreting this. Interpreting this means being able to write this. And even if you don't write it, you're thinking that. Okay, you see this thing that I put a cloud around, and you're thinking, oh, I'm adding up what I would get if I put I equals 1 in, and then if I put I equals 2 in, and I put I equals 3 in, and then I equals 4, and I kept doing that, and I added all those up. That's what this means. It's a value. It's the sum after you add them all up. So that's CI. So I trust BI. It's no problem then. Any questions on that? Okay, a partial sum. Okay, so now a partial sum is not the sum of all the terms, but it's the sum of the first n terms. So if we didn't want all the terms, but only the first so many of them, say n, then how would it change? What would change in this notation right here? Say I was going to do this partial sum for the sequence A. What would change in this notation right here so that I would only do the first n? I equals 1 to n. And then how would this change? Our last ... plus, not n, but what would we say? A sub n, right? A sub n, right? So now I'm taking the first n terms only. It's a part of the sum or partial sum, and that means I'm gonna add out to a n and not go any further. That's what we mean by the nth partial sum. So what is S2? What is S2? People are saying 4. Agree? S2 is 4. It's the second partial sum. It's where you take the first one and the second one and add those and stop. So the second partial sum is 4. So what we can do then is we can take these partial, so every sum has a bunch of partial sums depending on how far you go. What we can do is we can take those partial sums and we can make a list out of those, and then that's called the sequence of partial sums. So the sequence of partial sums means take every partial sum and make a list out of those, right? So take the first partial sum, then the second partial sum, then the third. Like this. S1, then S2, then S3, then S4. So for this A sequence 2i minus 1, for this A sequence, make the actual list of the sequence of partial sums. See if you can do it. So just create, what is this list? What is S1? What is S2? What is S3? What is S4? And then just make a list out of that. Meaning, just take the first, add up the first one terms of the sum. Okay, then S2. What is S2? Is it 3? 4. 4 means add the first two together. And what is S3? 9. Add the first 3 together. Then S4, 16, etc. Does it make sense? So this is going to take practice now. So practice thinking about it, doing examples, so you can really keep this all straight. So now it's getting a little more complicated. You've got to keep it straight, what things mean. So summary. Sequence, what? And a series, and then a sequence of partial sums. So we start with just a basic sequence. We can make a series out of that. And then out of that, we can make a sequence of partial sums. So here's an example of a sequence. Here's a new one. We haven't seen this one yet. 1, 1/3, 1/5, 1/7, 1/9, etc. what would the series be? So what would the series be for this sequence? Think like a second grader. Like a second grader, what would it be? Ramiro, what would the series, just to make it easy, how would you explain what the series is?
I would say 1 plus 1/3 plus 1/5.
Just add them up. Perfect. Just add them up. Okay? Now, sequence of partial sums. Sequence of partial sums means do what? Okay, so don't write, just watch. Watch and get this branded in your brain. Watch. Ready? First in the sequence of partial sums is 1. Second in the sequence of partial sums is 1 plus 1/3. So these are the partial sums. We're making a list out of the partial sums. Third term in the sequence of partial sums means add the first 3 together, and that's the third term. Fourth term in the sequence of partial sums. Add them together. I'll do the yucky part for you. Add those yucky fractions. Okay, then fifth term in the sequence of partial sums means take the first 5 terms of the sum and add those, and that's your fifth term of the sequence of partial sums. So then, just something to think about. We won't talk about it now, but what's the relationship between a series and a sequence of partial sums? What's the relationship between this sum and the sequence of partial sums?